On the 12th of August, millions of us stood still and looked up. We watched as the moon began to slide in front of the sun, a celestial dance that has captivated humanity for millennia. For a few precious moments, daylight surrendered to a profound twilight, and a collective cheer went up as the sun's majestic corona blazed forth in the darkened sky. The path of totality, that narrow ribbon where the sun was completely obscured, swept across the globe with incredible speed. It began over Greenland, painting its ice sheets with a fleeting darkness, before racing across Iceland, then through Spain, Portugal. For those fortunate enough to be within this path, the spectacle was breathtaking but brief. For most of Europe, it was a partial eclipse, a dimmer version of the main event. The real scientific prize, however, was in that fleeting total darkness, for it is only then that the sun's enigmatic outer atmosphere, the corona, becomes visible to us. On the ground, the total eclipse lasted for just a couple of minutes at best. This is a frustratingly short window for scientists who have so many questions about the sun. To truly understand the corona, they need more time. They need to stare into its ethereal glow to measure its light, to map its intricate structures. So they devised a plan not just to witness the eclipse, but to extend it. Instead of letting the moon's shadow race away from them, they decided to get in a very fast plane and fly right along with it, keeping pace with the cosmic spectacle. To keep up with the moon's shadow, you need something special, and NASA had just the thing: the WB-57 high-altitude research aircraft. This is no ordinary plane. It's a versatile and powerful machine, capable of flying at incredible heights, far above the weather and the thickest parts of Earth's atmosphere. Soaring at 50,000 feet, the WB-57 flew along the path of totality, its pilots expertly matching the aircraft's speed to the shadow sweeping across the planet's surface below. From this unique vantage point, the sky is a deeper, darker blue, and the view is simply unparalleled. By flying with the shadow, the science team aboard the WB-57 transformed a brief celestial event into a sustained observation. While totality on the ground might have lasted for less than 2 minutes in any single location, the view from the plane was stretched to nearly 3 full minutes. This extra time is invaluable. The plane wasn't just a viewing platform, it was a flying laboratory. Housed in its nose cone was a sophisticated suite of instruments, including 4 high-resolution cameras designed specifically for this mission. These cameras were working hard, capturing at least 20 detailed images every single second. They recorded the event in both visible light and in infrared, which allows us to measure heat. This flood of data provides an unprecedentedly clear and dynamic view of the corona, revealing the complex dance of superheated gas that makes up its structure. From that high altitude, the images are exceptionally sharp. The corona is one of the greatest paradoxes in our solar system. It is the sun's wispy, ethereal outer atmosphere, a crown of light that is only visible during a total eclipse. You might expect that as you move away from the sun's fiery core, things would get cooler. The surface of the sun, the part we normally see called the photosphere, is an already blisteringly hot 6,000 degrees Celsius. But something strange happens as you move further out into the corona. Instead of cooling down, the temperature skyrockets to an astonishing 1 million degrees or even more. This is the central puzzle that has baffled solar physicists for decades, the coronal heating problem. It defies our everyday logic. It's like walking away from a bonfire and suddenly feeling hotter instead of colder. Clearly, there is some unknown mechanism at play, pumping an enormous amount of energy into the sun's outer atmosphere. Discovering the source of this incredible heat is one of the biggest goals in astrophysics today. Scientists have several theories about what might be heating the corona. One idea: countless small explosions called nanoflares across the sun's surface. Each is too small to see, but together they could heat the corona. Another idea: waves of magnetic energy ripple up from the sun's interior, travel along magnetic field lines, and crash into the corona, depositing their energy as heat. Distinguishing these theories requires incredibly detailed observations of the corona's structure and dynamics. That's why extended viewing time from the WB-57 aircraft is so crucial. By watching longer, scientists can see how corona structures evolve. They can look for the subtle signatures of magnetic waves or the faint flickering evidence of nanoflares. High-resolution images taken in different wavelengths, visible, ultraviolet, X-ray, allow them to map temperature variations across the corona with incredible precision. Each new piece of data gathered during those precious minutes of totality brings us a step closer to finally solving the mystery of the sun's fiery crown. The result is a treasure trove of crystal-clear pictures showing the corona's delicate loops, streamers, and plumes in exquisite detail. Scientists can now meticulously study the shape and motion of these features, measure their temperature, and begin to piece together the physics of this incredibly turbulent and beautiful region of our home star. The chase didn't just happen at 50,000 feet. Closer to the ground, an international army of scientists was ready with another tool, balloons, in Iceland, in Spain. Teams prepared for a massive coordinated launch. They sent up around 80 high-altitude balloons in total, creating a distributed network of sensors rising through the atmosphere. These balloons acted as silent sentinels, measuring the dramatic changes that take place when the sun's light is suddenly switched off. They provided a completely different perspective on the eclipse's effects. As the moon's shadow swept over, the balloons measured fundamental properties of our planet's air. They recorded the rapid drop in temperature. They recorded the changes in atmospheric pressure. They recorded the changes in humidity. Some balloons carried instruments to measure ozone, a crucial gas that protects us from the sun's harmful ultraviolet radiation. Others were even equipped with cameras, pointed downwards to capture breathtaking photographs of the moon's shadow moving across the surface of the Earth from above. This data helps us understand how our own atmosphere responds to the sun's energy on a moment-by-moment basis. Proba 3 is not one spacecraft, but two, flying in perfect formation about 150 meters apart. One spacecraft, the Occulta, positions itself to block the brilliant light of the sun's main disk. The second spacecraft, the Coronagraph, follows in its shadow, using its sensitive instruments to study the faint corona. In essence, they create a precise, repeatable artificial eclipse on demand. This incredible feat of engineering provides a view of the corona that is impossible to get from Earth. Because Proba 3 operates in the vacuum of space, its observations are completely free from the blurring effects of our atmosphere. It can study the corona closer to the sun's limb than most ground-based telescopes are able to, revealing a critical region where the solar wind is born. By combining the data from Proba 3 with the observations from the WB-57 and the balloon launches, scientists can build a truly comprehensive, three-dimensional picture of the corona and its influence on the space around it. All of this effort, high-flying planes, the legions of balloons, the formation-flying spacecraft, is for more than just scientific curiosity. Understanding the sun is a practical and vital necessity for our modern, technology-dependent world. The sun is not a calm, steady ball of light. It is a dynamic and sometimes violent star, and its activity directly impacts us here on Earth. The same corona that we study during an eclipse is the source of the solar wind, a constant stream of charged particles that flows outwards through the solar system. This solar wind coronal mass ejections can have significant consequences. These events can buffet Earth's magnetic field, creating what we call space weather. Severe space weather can disrupt our communications satellites, knocking out GPS signals, television broadcasts. It can pose a danger to astronauts in orbit, who are outside the full protection of our atmosphere. In the most extreme cases, it can even induce powerful electrical currents in our power grids on the ground, leading to widespread blackouts. By studying the corona in detail, we learn how these solar storms are born. We can see the tangled magnetic field lines snapping and releasing a burst of particles into space. The more we understand the physics of the corona, the better we can become at forecasting space weather. Just as we have learned to predict hurricanes and tornadoes on Earth, we are learning to predict storms from the sun, giving us time to protect our vulnerable satellites' astronauts' electrical systems. So, when we stare in wonder at a total solar eclipse, we are looking at the very source of the space weather that shapes our cosmic environment. The beautiful, ghostly light of the corona is a reminder of the powerful and complex connection between our planet and its star. The work done during those few minutes of darkness helps protect our way of life and deepens our understanding of how stars work throughout the universe. The 12 August eclipse was a fleeting spectacle, but the knowledge we gained from it will last for a very long time. This wasn't just about pretty pictures, it was a mission to understand the star that gives us life.